So we are starting a new chapter, infinite sequences and series. This is the most interesting topic of the book. So today we'll start with sequences. So the plan of this chapter, first we will study sequences. So in everyday language, sequence is an ordered set of infinite numbers, infinitely many we'll try to make this a little bit more precise. But in everyday language, we can say that you have this sequence of the numbers where, of course, there has to be a way of determining the general term. Okay, so a sequence will not be determined unless we know how to find every term of it. Okay, so this so if you say I'll throw head and tails every time, and the nth term is the result of the nth outcome. Okay, so we will not take it as a sequence. Okay. Here we will be interested in what happens to the terms of the sequence as we go towards infinity. Okay, we have infinitely many numbers. Do they try to reach to a limit or not? We'll make the concept precise, but okay, in our minds, we understand that, for example, 1 over n becomes smaller as n goes to infinity, so the limit there will be 0. We'll try to understand this. Okay. The reason we try to understand is because using this, we'll look at infinite sums. Okay, so another name for this is series. Okay, so here I add a number, then I add another number to it, and then I add another number to this. Okay, so you see I get a sequence. I'll keep adding numbers here, so I'll have an infinite sum. So does this infinite sum make sense or not? In order to understand this, I will import techniques that I learned in sequences. Okay, once we have this understanding for numerical infinite sums, we'll look at power series. So this is infinite sums where each term depends on x, let's say, on a variable. Okay? By changing the variable, you change your infinite sum. So for certain values of x, the infinite sum will add up to a number. For certain other values, it will not add up to a number. We'll try to understand this. Okay? So in order to understand this, of course, we need information from here, because every time x is fixed, it will be a numerical series. And here we know when a numerical series converges or not. So we'll impose it here, and then it will give us some conditions on x so that the infinite sum converges. Okay, so far this is just fun, but this is the main part. Here is now associate Taylor series. So associate power series to a function and check if that power series represents this function or not. Okay, so this is the part. This was the most spectacular success of calculus when it was first invented. Of course, you have this derivative integration, gravity, etc. But the most sensational success of calculus was in this part, because you can now write sine x equal to an infinite power series. And the advantage of this part is taking information from here and applying here. Of course, nobody can add infinitely many things. Okay? We know that if you add that infinite power series, it will be precisely sine x. But since I cannot add it, how do I use it? If you add only the first 5 terms, there's a way of knowing precisely how much error you are making. Right? Precisely in this sense means that you know that your error will not be larger than a certain value. If you want a smaller error margin, you add a few more, but you definitely know where to stop. Okay, if you want to calculate the value of sine of 1 degree, which has been an important concept, important problem in navigation, of course, we have to find ways of calculating sine of 1 degree using approximations. When you make an approximation, you don't know how much error you are making. But with this technique, if you say, I want to calculate sine of 1 degree, and I want the error to be less than 1 over 1 million. Okay? Then we know how many terms you must add in the power series so that the number you get is sine of 1 degree, and the error is strictly less than 1 over 1 million. You don't like 1 over 1 million, make it 1 over 1 trillion. Okay, then we add a few more terms, but we know exactly where to stop. Okay, so sine, cosine, tangents, exponential functions, and in particular logarithms. Okay, so now this is not important for us, but we use it at some other places. But the actual use was then to calculate logarithm tables. All calculations were done using logarithms. Okay, you have to use logarithm tables, just like you are using your smartphones. Okay. How do you prepare those logarithm tables? Okay, so people were doing approximations. Now, with this technique, we know precisely, since you are, for example, your logarithm table will have 4 digits. Okay, so your error will be less than 1 over 10,000 or something like that. Okay, so you know you can calculate logarithm of anything using. You don't even need a table now because you have a formula. Okay, you can calculate the logarithm to any degree of precision. Okay, so our aim is to come to this part, and since we don't have that much time, so probably we'll mention this in the last week. But here, in particular, here we will talk about alternating series. So that's the most easy. That's the easiest thing. It looks like a fable, but it holds. If you add something, subtract something, add something, subtract something, and if these numbers are getting smaller, then if you stop at some place, the error you are making is less than the first term you didn't use. Okay? So you say, where will I meet this? Okay? So when you come here, most trigonometric functions have power series obeying this rule. So when you stop at a stage, the first term you are not using tells you an upper bound for the error. Okay? So it's that easy. So we'll mention these things. We'll tell how when this method works. Sometimes it doesn't work because you can associate a power series to a function, but the power series has nothing to do with the function. Such functions exist. Okay, so that's why we will invent a new name here. We will call nice functions analytic. They are equal to their Taylor series. Okay, so this is the plan. This is what we want to do. So we'll start with the sequences. So we'll go through this as if it's a game at each step until we come here. So the series part is here. Then we'll look at sine, cosine, and other transcendental functions. Okay, so what is a sequence? So technically speaking, a sequence is a function from integers, okay, let's say from integers to real numbers. Okay, so here there is 0. Sometimes you use 0, sometimes you don't. Okay, so I will be flexible there. So this is the technical thing. So you see that this conveys this pedestrian way of thinking about sequences. We have infinitely many of them. Okay, so for each integer you have a number. They are ordered because you see you will have integers ordered here, and the corresponding values will be ordered by these things. But we don't show sequences by f of n plus 1, etc. There's a traditional way of denoting sequences. Okay. Of denoting a sequence. Okay, so we denote it. Sometimes we start from 0. Okay, so this goes on. The nth term is denoted like this. It goes on, and there should be, so since it's a function, it is defined everywhere. There is a rule. So that translates here that you should know how to calculate this. Okay, so these are real numbers. Okay, so these are all real numbers in calculus. So next year, if you take complex analysis, there will be complex numbers. So you also have a sequence of complex numbers, but we'll stick to real numbers. Okay, so sometimes you don't want to start with index 0. So we can say our description makes sense starting from 3. Most of the time we start from A1. Okay, so this starting part, the beginning of this is not important. As a function, it is important, of course, the value of the function at every point. But for a sequence, what is important for us is what happens as you go in this direction. What are these numbers doing as the index increases? Okay, so according to this thing, so this thing is if you have a function, say if this function is f, then this thing is f of n. Okay, but we don't like this notation. Okay, so this is how we want to denote the numbers. We just write, in real life, you just write numbers here, and then you give a description of how the sequence continues. From that description, we want to understand what we will see as we go here towards infinity. Okay? So, for example, one interesting thing in the book is the following. So, example. We have a sequence starting from 1. So, A1 or A0 is 1. A2 is 2, 2. I put 2 2s. Then I put 3 3s. Okay, so this goes on like this. Then I start with 4. And at some point, I have n minus 1. Then I start putting n here. And then I have n plus 1. So here I have n of them. Okay, so this is A1, let's say. This is A2. This is A3. This is A4, A5, A6. Okay, so the question is, okay, think of a number, 2017, every year you can think of something here. Okay, so what is A of 2017? Okay, so we gave a full description of the series. We didn't give a formula for the nth term, but we described the series. The series is well defined. Nobody has any ambiguity about this. So, okay, so if you have the patient, you can put all these numbers and count them, and when it comes to 2017, you'll know what number it is. So, but that is not science, that's not engineering. Okay, so you have to do this, you have to calculate this before anybody tries it. So, what do you say? Okay, so you see this is 1, the term 1, index here. Then this is 3. Okay, so I'm putting these indices here. This is 6. If we go with 4s, then the last 4 will be 10, right? Yeah, you agree? Because I put 4 4s here. It was also 6, 7, 8, 9, 10. Okay? So the last index, the index of the last term after I start adding something and before I pass to the next thing are these numbers. And these numbers have a formula, right? Summation. You see, this is summation of 1, 2, 3, 4. Okay? So what is this one here? The last entry of n minus 1. You add up all integers from 1 to n minus 1. n minus 1 times n over 2. What is this? What is the index of this? So let me say these are indices. A, K. So these are K's. These are K. Okay. So this one is now n plus 1 over 2. Right? Okay. So continue from here. Well, this is the question. If this index, so you see these red ones are indices. If this index is between this and this, what must the n be? Okay. Let's change color. So this says that A 2017 is equal to n if this index 2017 is less than or equal to n plus 1 over 2 and strictly larger than, it must be here, okay, n minus 1 n over 2. Okay, so now you can either guess, do a few trial and error, or you can solve an equation. Okay, so you can say this is equal to this. What is n? N is going to be, of course, some fractional number. I think it, and then you try around that. Or if you want to be precise, draw the figure. So that will be 63 point something. But I need integer, so you go up. The first integer is 64. Okay, so here it turns out that n is equal to 64, I think. Okay, so I think I calculated this, so I can check. No, I didn't bring these things. So, okay, so this is how we calculated this. Okay, one example. Normally we have a formula for an, so that will make it easy to find what the general term is. Okay, so of course we are interested in the limit. So let's talk about the limit. Limit of a sequence. Okay, so we are interested in the limit of a sequence. Again, let us remember why we are interested in this. We'll look at infinite sums. Okay, every time you add something, okay, you cannot add infinitely many things in one lump. You will add them one by one. Every time you add something, you obtain a new number. That's a term of your sequence. Then you add another number, you get a new sum. Okay, so if these sums, if these sums converge to something, we will say that this infinite sum is equal to this. Okay, so we all know, for example, the geometric infinite sum converges to something. Okay, so we will not every infinite sum is nice as a geometric sum. Okay, so there we will obtain strange formulas for the general term, and then we will use these techniques to find the limit. So that's why we are interested in finding the limit of a sequence. But you can forget about this objective. You can look at this just as an intellectual pastime, just like Sudoku. Okay, so we have a sequence. How do we find the limit? But first of all, let's technically talk about the limit. So first I'll give the technical definition. Okay, when you are in trouble, you go back to the technical definition, and I'll explain it. Most of the time we use that. We say limit of a sequence an as n goes to infinite is equal to L if the following holds. So first of all, let me just say this. For every epsilon positive, there exists, well, okay, let me not use this notation. There exists an index n such that whenever n is larger than or equal to this fixed index, we have the difference between L and an is less than epsilon. Okay? So what does it mean? It means that we have this infinite sequence. Okay, so this means the following. So we have this thing, an, and then we have more terms here. Okay, these are fluctuating, going up and down, but we realize that they seem to be dancing around a number. Okay, so we claim that that number is L. Okay, so we claim that the limit is L. And you say you'll believe this if all the numbers from some point on, if all the numbers are around L, and you will be happy if the difference between the number and L is less than, say, 1 over a million. Okay? Then I'll look at this series and I'll say, okay, from this point on, take all these numbers. The difference between each number here and L is less than 1 over 1 million. Okay? Then you say, I changed my mind. 1 over 1 million is not good enough. I'll make it larger. Okay? So 1 over something very large. Okay? Then I'll find some other place here. All the numbers from here on up to infinity, each of them is close to L, and the difference is less than what you specified to me. Okay, so this epsilon is your degree of happiness. Okay, so you say you will be happy if each an lies in a neighborhood of epsilon, in an epsilon neighborhood of L. Okay, so this is on the real line. This is L. Okay, so this is L minus epsilon, L plus epsilon. If ANs are such that all ANs lie here, you will be happy. Okay, so and then you say, okay, I'll accept L as a limit. Okay, then I find N such that if you take any AN with index larger than or equal to N, then AN will make you happy. Okay, so AN will be here or here. Okay, so if I can always deliver you this index, whichever epsilon you give me, then we will all agree that L is the limit. Okay, so that's what we expect from a limit. Most of the time, in most sequences, AN never sees L. Okay, so it can never be exactly L. If it's sometimes L, it's easy. Okay, so we say the sequence collapses and it becomes constantly L, then everybody knows that the limit is L. Okay, for example, if AN is given by the formula 1 over N, as N goes to infinity, this thing becomes smaller and smaller. It is smaller than any positive number. So we say the limit is 0. Okay, but the sequence is never 0. It will never see 0. It will always come closer to it. Okay, and it will come, the distance between the terms of the sequence and 0 will always be less than any number you give after a certain index. I'll always find an index here so that 0 minus 1 over N in absolute value will be less than your epsilon. Okay? So this is what we mean by the limit. So for example, this sequence has no limit. Okay? Because this sequence goes to infinity. Here, L is a number, so maybe I make that note. That's the terminology. Okay? Recall, here, L is a real number. L is not plus or minus infinity. Okay? Sometimes we say that the limit of the sequence is infinite. For example, here, the limit is infinite. Okay, so that's abusing the terminology. Technically, if the limit is infinite, we say the limit does not exist, because when limit exists, we have theorems. Okay, if the limit exists, then you can do this and that. But if the limit is infinite, you can't do these things. You can't do these things means, of course, nobody is preventing you. You can do these things, but the numbers you get will have no relation to the question you have in mind. Okay? So in order to make these things clean, every time we have a theorem about limits, instead of saying when the limit exists, but when it is different than infinity, then you can do this and this. To save time, from the beginning, we say when the limit is infinite, we say the series diverges. Technically, we should say the series diverges to infinity, but nobody does that. Okay, so that's, we say the limit is infinite, but the limit does not exist. Okay, that's how the terminology is. So let me mention that also, because to know that the limit is infinite is an extra information. Even though the sequence is diverging, we know its behavior. We want to use that extra information. So limit an as n goes to infinite is equal to infinite or minus infinite if for any number m there is an index n such that when n is larger than that index, an is larger than m, or larger than or equal to m. Okay? So this means that the sequence is unbounded. It goes to infinity. Okay? Technically, we should say the sequence diverges to infinity, but we say the limit is infinite with the understanding that the limit does not exist. But we don't treat this case, we don't treat this an, this sequence, as a convergent sequence. Okay, so terminology, let me. If limit an as n goes to infinity exists as a real number, like there, we say an is convergent. Okay, so that's the terminology we use. Or we can, if we know the limit, we say the limit, the sequence converges to L. If limit an as n goes to infinite equals L as a real number, we say an converges to L. Okay. If no limit exists as a real number, then, so in R, then we say an is divergent. Okay, so all theorems about sequences will be about convergent sequences, and if the limit is infinite, those theorems don't work. So that's why we are trying to make this distinction. Okay, so you see, we are interested in finding the limit. The definition of the limit is very precise, very nice. Everybody understands what's going on. But once you get the shock of or the amazement of its beauty, you realize that it's a useless definition, because how do I find L? Okay, so the question is to find L. By looking at this definition, the only way is you try all possible real numbers here and check if it's going to be the limit or not. Okay, so since that's not going to be possible, then we must have methods of finding the limit. Okay, so this is where this touches the other techniques in calculus. Okay, we'll go to functions, and everybody loves to use L'Hopital, etc. So it will be used here legitimately. So let me follow the book. Okay, so this is the time you talk about functions. Okay, so now the question is, we understand what a sequence is. We also understand what the limit of a sequence is. And we all agree that finding the limit of a sequence is important. So how do we find the limit? Okay. So how do we find the limit of a sequence? Okay, so the whole section on sequences is giving techniques of finding limits of sequences. So the first thing is, if there is a function f of x such that f of n equals a n for integers, for positive integers n, and if limit f of x as x goes to infinity is equal to n, okay, then limit a n as n goes to infinite is equal to n. Well, this is obvious, okay? Because you see, if you want a formal proof, this is the formal proof. Here we are looking at the limit. Limit exists. If the limit exists, then all spatial limits exist. Now, instead of choosing this x freely in real numbers and sending them to infinity, I choose x only a subset of R, integers. Okay, I send x only through integers to infinity. Then it should be L again. Okay, so this is this is why we made those theorems about limits. At the time you do it, it sounds so trivial that why should you mention that? But it becomes crucial here. Okay, now this is, well, once this is over, you see that this part is calculus. Okay, you have a function. If the function is differentiable, we have lots of methods to understand the limit. So I will come to this. So let's see. And just like taking derivatives, remember if you look at the definition of a derivative, it's a complicated expression. Something over something, you have to take the limit, and both the numerator and denominator of this something over something goes to 0. Okay, so you have to do cancellations, etc. But we showed that sum of a limit is limit of some derivative of a sum is sum of derivatives. There's a rule for product. There's a rule for quotient. So all you have to do is actually use the definition of derivative to calculate the derivative of 1, which is easily 0, and to calculate the derivative of x, which is 1. Okay? Then combining these things, you can calculate the derivative of any rational function. Okay? And derivative of trigonometric functions all relies on calculating the limit of sine x over x as x goes to 0 as a radian measure. You calculate this limit as geometrically from figures. You find that that limit is 1. And then all derivatives of all other trigonometric functions follow, again, formally from these combinations. Okay? So actually, the only thing you calculated there was the derivative of 1 and derivative of x. Okay? And here it's the same thing. We have to break this up into small parts. So we have the usual rules. So let me say the usual boring theorems, facts. Okay. So limit a n. So suppose that limit a n as n goes to infinite is a. Limit b n as n goes to infinite is b. Okay. Then limit a n plus b n as n goes to infinite is a plus b, the usual thing. Okay, so here you see that a and b cannot be infinite, and these things will not make sense. Okay, and you have limit a n b n is a b. So let me write etc. here, because those things are obvious. You can divide a sequence by another sequence. Here, okay, let me make one more remark here. So limit a n over b n is a over b if b is different than 0. Now some of these bn's may be 0. Okay, at the beginning, there may be a million bn's dispersed around the sequence which are 0. So an over bn is not defined when these things are, when bn's are 0. But if the limit of bn's is b, and b is different than 0, the limit tells me that bn's are, from some index on, bn's will be close to b. Since b is different than 0, from some point on, all bn's are different than 0. Okay? They are approaching to a non-zero number, so from some index on, they are all non-zero. They are around this b. So this side is intended to calculate an over bn from that index on. Okay? So this n goes to infinity. You start writing an over bn from the point on when no more zeros appear in bn's. That's the understanding here. Okay? So you don't give up. If at the beginning some of the bn's are 0, you don't give up here. So the meaning of this is that you calculate this later. You see that in all these things, the important thing is what happens to the sequence when the index is large. We call it the tail of the sequence. A tail of the sequence is not a well-defined concept because we don't specify an index and say that from this index on up to infinity, that's the tail. Tail is just when the sequence starts to behave regularly. Okay, up to a point, it may go up and down, it may be minus, 0, whatever. And from some point, if it has a limit, from some point on, it starts to remain inside an interval here. Okay, so that part is called the tail of the sequence, in short. So we use that term to say that we are interested in the behavior of the tail of the sequence. Okay? So these are all what the tail of the sequences do. So you can multiply these by constants, etc. So if you have this function, if this is a complicated function, then you look at its sums. Each sum may be product of certain things or ratio of certain things. So again, all you have to calculate is, limit of 1 over n generally, that goes to 0. And the limit of a constant is constant. So these are the only technical things that you calculate. Okay, so and we have the squeeze theorem for limits of functions. So another thing, the squeeze theorem or sandwich theorem. Okay. So we have three sequences an, bn, cn for n large enough. Okay, generally that's what we say. What we mean is there exists an index n sub 0. So for all indices n larger than or equal to n sub 0, we have this inequality. Okay, so when we say this, when for all large n, we have this inequality. So if we have this, and limit an as n goes to infinity is the same thing as limit cn as n goes to infinity, and suppose that's L, okay, then limit bn exists, n is equal to n. Okay, so this is generally useful as you go back to calculating limits of functions. This is useful when this thing wiggles around a lot. You can't control its behavior, but you have two nice guys from squeezing it from both sides, then you control, then you understand the behavior. Okay, so, and of course, an application of this is when you suspect that the limit is 0, and there are some plus or minus signs, you can get rid of that. That's an application of this. Okay, so this is 3, so let's say 3 prime. If limit, well, actually this is both sides. Okay, so let me say limit an as n goes to infinity is equal to 0 if and only if limit n goes to infinity absolute value of an is equal to 0. Okay, so here you see that an is either equal, or rather this thing is either equal to an or minus an. Okay, so this is either here or here. So if this limit goes to 0, if these things go to 0, then this will go to 0. Okay, and of course, if an is going to 0, then its absolute value is ideally going to 0, right? So we generally use it in this direction. Okay, so the general application, because when you take absolute values, then there are some annoying sign conventions. You throw them away. You just deal with the actual behavior. And of course, when this function is nice, if it is continuous, we can we can also have some nice things. So that's another theorem. Okay, so you see here, the idea of this thing was to build new sequences from old sequences, okay, so like sum, product, etc. So you can immediately find a rational function of this. So then when we compose the functions and we know the limits of each part, then the limit will be composition of those things. And that's generally expressed in this way. If limit an as n goes to infinity is equal to L, and f is continuous, then limit f a n as n goes to infinity. You see, this is composing of two things. You have a nice sequence an, and then, I don't know, for example, you take the sine of this. Okay? So these techniques don't tell you what's happening, but we immediately notice that since sine is continuous, you can take the limit sign inside. That's one technical definition of a continuous function. The function and the limit operation change places. Limit goes inside, and I know the limit of this, L, so this is equal to f of L. Okay, so instead of working with sine of an, you just work with an, and you take you evaluate f at that limit. Okay, so these are, some of them are obvious, but okay, so that's obvious. So let me mention these two things. So there is this monotonic sequence theorem. I mentioned that, and then we'll stop. Okay, so definitions again. We need these definitions because such sequences show up, and instead of describing them every time, we give a name to this. Okay, so a sequence an is bounded from above if an is less than or equal to m for some m, a real number, and all indices n. Okay? And instead of this, you can say below if an is larger than m for some m and all n. Okay? A sequence is bounded, an obvious definition. A sequence is bounded if it is bounded from above and below. Okay? And we have increasing and decreasing. Again, definition, and then I'll quote a big theorem and we'll stop. Okay? A sequence an is increasing if an is less than an plus 1 all n, decreasing if an larger than an plus 1 all n. If it is decreasing or the increasing, we say it is monotonic. Now, if you want to refer to other books, you will see that these definitions are not universal. Sometimes when we say increasing, you allow these things to be equal. Sometimes, in some books, they define a sequence as increasing if an is less than or equal to an plus 1. And to imply strict inequality here, they say strictly increasing. Sometimes instead of increasing, they say non-decreasing to confuse you more. Okay, so just beware of those terminologies. But the idea is this, okay? So this sequence eventually becomes larger and larger, or the sequence becomes eventually smaller and smaller. And now we have the big theorem. This is monotone bounded sequence, or whatever the name is. Let me check the name. Monotonic sequence theorem. Now we say monotone bounded monotonic bounded. Let me write it. Bounded monotonic sequence theorem. Every bounded monotonic sequence is convergent. That means it has a real limit. Okay, it doesn't go to infinity. It doesn't dance around different numbers. It converges to a real number. Okay, so the real number, if it is increasing, for example, if it is increasing, then you consider the set consisting of all elements of the sequence. Then one axiom of real numbers is every bounded set has a least upper bound. The least upper bound is the limit of this. Okay, so there's a short proof in the book, but you can figure out what's happening. If it is decreasing, you look at the greatest lower bound. Okay, so that will be the limit of this. Again, you see we have a theorem which tells you that the limit exists, but it doesn't tell you how to find the limit. But this is surprisingly very useful, because in most cases, we will be able to say that after we do blindly some algebraic operations, we'll say that if the limit exists, it is equal to 5. And in some cases, the limit does not exist. But if the limit existed, it would be 5. How do we know the limit exists? This is probably the only tool we have. Okay, if the sequence is behaving nicely, if it is increasing, then we know that the limit exists. Now apply your algebraic tools blindly. What will you find? You'll find if the limit exists, the limit is 5. Well, this says the limit exists, so the limit is 5. Okay, so these two things are different. At first, you say, if I find that the limit is 5, it is 5, but just consider the sequence. I'll give the sequence again next time. You start, say, with the 5, okay? And then each next term is reciprocal of the previous one. Okay, so if you blindly apply the algebraic rules to this, so I think you'll find that the limit is square root of 5 or something like this. Okay, but the limit does not exist. It's 5, 1 over 5, 5, 1 over 5. It's not approaching anywhere. Okay, so you see, you have, okay, I'll do this next time. Today, let's stop with this nice theorem.